I'm sorry, but I'm experiencing problems with my.
Press again. एक बार प्रेस करके लगाइए।
Thank you for solving the issue. Yeah, sorry, but we had some. So I'm sorry, but I had some issue with the laptop, and I solved it thanks to him. So now let me wrap up on the discussion about the levels, which we went through in the first part of the morning, and let's now move to what they want to do with this data. Obviously, the final goal is that of obtaining a specific type of information from remote sensing data, but this is not necessarily always one-step process where you put data into an algorithm, and this data is processed in always the same standard way to give you the final information that you're interested in. But very frequently, especially if you're working in a research environment, you may need to play a little bit with the data in order to make this information better visible or in order to make it emerge from the mass of data that you generally have to deal with. So I thought it would be useful to see some basic tools that can operate on the data in order to change it from one form to another one, which is more useful for your purposes. So you can either call them basic tools, or you can also call them transformation. Transformations doesn't mean, in this context, transformation doesn't mean necessarily something like the Fourier transform. I'm not talking about that. I'm talking about changing the way the data is represented in such a way that in the new form, the data is more useful for your purposes, okay? So it can be deriving a data set from the original one, which highlights certain features of the data. It can be rewriting the data set in a manner that is more useful for you. We'll see both ways. I will go pretty quickly through this section because I think many of you will have heard about these tools at some point, especially if you're working with scientific data. But we will see them in a context of remote sensing for Earth observation. So looking once more at our scheme, we basically now we found ourselves between the data and of which we have said almost everything, between the data and the interpretation process. We're not yet directly extracting the information products that we want to deliver to our users. We're still reworking the data in such a way that the next stages will be easier or more effective. Okay? So one very simple operation that is frequently beneficial in Earth observation is thresholding. What does thresholding mean? As I said, this is something which is common also in other disciplines. So thresholding means applying a threshold, which means that you set a value and anything that goes below that value gets classified in manner A, and then whatever goes above the threshold gets labeled with class B. So in mathematical terms, very simple mathematical terms, this means that you have a data set, a starting data set, a source data set, and then you have generally a different data set, which is derived through this operation. So this is an important point. It seems trivial, but it's not. You don't destroy the original data set. You generate a new one. Okay, so this is pretty common. When you start from a data set, it generally sits there, especially if you're working in a remote sensing environment, in a research environment where you don't know exactly what will be the best strategy. You will keep the original data set intact, and then you will derive the various steps, because in this way you can roll back if you realize that you didn't you didn't take the right step. So in the case of thresholding, you simply compare the value with set threshold, and you will put here two values, typically 0 and 1, to mean which of the case is there. Why is that useful in remote sensing? Because frequently, we're talking about scalar data, okay? So when we take something as an input to a thresholding operation, obviously you need a scalar input in order to be able to do this comparison. So scalar input is not, the typical data set that you get is a multi-component data set. You have multiple bands, right? remember the filing cabinet. You pull a drawer and you find multiple numbers. Which one are you supposed to compare? This is the reason why you generally focus on one of the spectral bands. So you don't take all the levels of the matrix, but you choose one which results into a single level matrix, and then you do the thresholding on that matrix. This selection obviously is guided by the physics. When you do thresholding, you select one specific band because you know the information you're seeking lies in that band. Let me give you an example. If you want to identify vegetation in a data set, one very simple way of doing that, it doesn't work in 100% of the cases, but one very simple way of approaching the problem is look at the physics. We have seen at the beginning of the course that vegetation typically has a very high reflectivity in the near infrared region, right? So if you look around 700, 800 nanometers of wavelength, where there's vegetation, there's a very high response. So you look at the folder with all the possible bands and you say, okay, let me approach the problem in a very simple preliminary manner. Let's unfold. Let's take out the one band which sits at around 7 to 100 nanometers, and we'll do thresholding on that band. Okay. We set a certain threshold. We can adjust it based on on the feedback that we get as a result, and whatever lies beneath that value, we assume it's not vegetation. Whatever lies above the threshold is vegetation to us. Okay, so very simple. Like in this case, this is a different example. This is a radar data set, and water in radar data sets typically provide very low response. So if you threshold with a very low value, then you get a binary map in which zeros represent water and ones represent other types of land cover. Okay, there's not much to discuss because it's a very simple thing. Okay, it's nothing fancy. But still, in some cases, it can solve you some problems. Typically, it is used to specialize processing. It's not a very effective way of distinguishing land cover classes. Like I made these examples because they are very easy to understand, but typically you will use this to specialize further processing, not as a way to produce your final result, because in many cases, if you use it for land cover classification, it will turn out not to be very accurate. Okay. There's also, if you have used this in other contexts, you probably have learned that there's a criterion called the Otsu criterion, which basically tries to guess the optimal level of threshold given the distribution of data. Okay, there's nothing fancy in this either. It is used in remote sensing also. Okay. Another thing which is maybe a little bit less common in other disciplines is maths. So is using simple mathematical operation across multiple data sets in order to combine them. This is, in some sense, this is a very simple case of data fusion. When you have 2 data sets and you combine them by applying very simple mathematical operations. Obviously, this operation makes sense if you have 2 perfectly matching, in spatial terms, 2 perfectly matching data sets. Otherwise, you're mixing things that have nothing to do with each other. So the first requirement here is that you have 1 and 2 data sets that are perfectly overlapping. And this can be done, this can be granted, for example, when the 2 data sets are simply 2 different levels of the same matrix. Okay, so even if you have 1 single acquisition, you can still use this approach because, for example, you want to combine the information contained in 1 layer with the information combined in the other layer. And I will give you an example a few slides down the line. What operations can you implement here? Well, one is the sum. You may want to sum multiple images. From a physical standpoint, it doesn't make a lot of sense because, remember, again, if you roll back to the beginning of the course, what are you measuring? You have an instrument flying in space and looking down, and you do very refined correction and everything to get to an estimate of what? No, a physical variable. You want to estimate what? Yeah. No, you're talking about applications, but I'm talking about the physics of the process. So reflectance values. Yes, what is reflectance? The ratio, yes, right. It's a ratio between 2 amounts of energy or amounts of power, depending if you want to take the time into account or not. Let's say it's a ratio of powers. It's an energy efficiency, right? So your basic data item is, physically speaking, it's an energy efficiency. Does it make sense to sum? Does it make sense to sum etas? No, not really. It only makes mathematical sense, but not physical sense. Okay, so why do we do this? Why do we want to sum energy efficiency? Because it makes sense in a mathematical context. Because if you sum values from multiple acquisitions, then you can also divide that sum by the number of acquisitions, and you can basically average the measurements. From whatever discipline you may have learned in your studies, you know that when you have a measurement affected by error, especially if the error is balanced, so it has a probability density function which is at least roughly symmetrical, then you can get an estimate of its expected value by taking its average, right? So the more you average, the closer you get to the expected value of that random variable. And Earth observation is no exception. You do measurements, repeated measurement. Remember, one more important element here. These are all repeated measurements done in approximately the same conditions, but especially from approximately the same viewpoint with the same geometry, same everything. So basically, you're doing the same measurement multiple times. So you have this resource in your hand. You're measuring the same thing, or supposedly the same thing, multiple times. You can average the measurements to get a better, a more accurate estimation of the variable. Now, in order to give you a visual example, I had to resort to radar data because in optical data, the noise the noise that we're trying to kill with this operation, not the atmospheric disturbances, which is a different department, but the actual noise, so the small perturbations that are inherent in measurements. Generally, in optical data, these are not visible. Okay, if you take a visual representation of data, you can't see the noise. You can see other sources of disturbance, but not a real random noise. Okay, great. So I took radar data. This is not radar data, this is optical. It's the optical representation of the area, which is the Linate Airport next to Milan, close to where I live. The radar acquisition of the same area is represented here, and you see it's very noisy. I mean, if you look at the image, radar data, we will see that on tomorrow. Radar data is characterized by having a very high level of noise. Let me summarize it very briefly now. Unlike optical data, which looks very smooth, this looks very rough because every pixel has a random variation in its backscattered recorded value, which visually results in this very rough appearance. Okay, so we have visible errors here. If you take the same acquisition in multiple orbits on the same area, under the same conditions, etc., and you sum them and you average them, you get something like this, which visually is very much cleaner than the previous one, right? Why? Because we basically, by averaging, we compensated the random variations because they killed each other. And we got to a stable average on every single pixel, which reports much better the actual reflectivity of the object which we are observing. Okay, so this is one more basic operation that you can decide to do before moving on for further processing of the data. Obviously, it's not all good. When you average, you should remember that you're not doing exactly the same measurement because the clock rolls and the distance between the acquisitions may be days or it may be even months. So things may change in between. So you have to be careful when you do this operation. Never forget. Never forget. This is part of the basic message. Never forget that you're not dealing with pure numbers. You're dealing with physical reality of objects. So always keep in mind that you're working on the real world, okay, not on pure data. Anyway, this is operationally done, and it's a very useful basic tool.
Here, why we always follow Gaussian?
It's not Gaussian, actually. It doesn't actually need to be Gaussian. In the case of optical data, it tends to be Gaussian. It tends to be Gaussian, but it's not exactly Gaussian. In the case of radar data, it's not exactly Gaussian. It's Rayleigh distribution. However, the Rayleigh distribution is approximately, the approximate Rayleigh distribution that you observe in radar images is evenly partitioned between plus and minus. So if you average, you get an effective reduction of noise. But it's not Gaussian. Okay, it's not necessarily Gaussian. The requirement is that the area beyond the center of weight is same, approximately the same as the opposite. Yeah, yeah. And obviously, this worked out because there were no significant changes in the time. 60 images for this satellite meant about 5 years. Yeah. So you see, you need to be confident that nothing relevant happened in that time span. Otherwise, it doesn't work. Or it works anyway, but it gives you errors.
So it is not of city.
No,
It's not of city.
no. Okay, so yeah, then you may also have image differencing, which is useful for change detection. I don't want to spend too much time on this, but if between two acquisitions, nothing changed, then the difference is called, yeah, the difference between the corresponding elements should be 0. It is actually never 0 because you still have errors, so you should allow some tolerance in the difference, so it doesn't need to be exactly 0. It may be small, where small is defined as smaller than a certain threshold, and then whatever significant change there may have been between the two acquisitions, then it activates a flag on the so-called change image. This is typically used as a basic step, as a first step for the problem of change detection, which is typically in Earth observation. You have an acquisition before a certain event, an acquisition after. Like, for example, you have an acquisition before a flooding event, an acquisition after. Whatever has changed probably indicates the area that were affected by the flooding. But it may also be like before and after harvesting, where has harvesting took place, where did the harvesting took place, etc. Yeah, like, yes, this is an example of flood detection where we used radar data. This is in our area. We used radar data before and after a flooding event. We subtracted the permanent water, which is that of the river. This is the River Po. It's the largest river in Italy. You have, this is before a flooding event, and this is just during a flooding event. As you may see, water is generally very well visible in radar data because of the reasons we will see tomorrow. So when it floods out of the river bed, it also becomes very visible. You can easily get a map of the flooding because water is very well visible. But if you simply map water in this image, you will get a map of the flooded area plus the river. So you have to subtract the river. So you map the river before, then you map the water after, and then you subtract the two masks. So flood minus river, and you get a map of the flooded area. So this is a very simple exercise that I show to my students to illustrate why these operations can be useful. Then there's also image multiplication, but it's very rarely used. It's generally used to multiply by 0 in order to remove objects that are not interesting for your application. But more interesting is image division, when you divide one matrix by another. Why is that interesting? Because this is an example of a case where this type of transformation can really highlight the type of information that you may be looking for. So, for example, you already know, I always stumble into this example of vegetation. You may know that vegetation has a strong response in near infrared and a very weak response in red, right? But vegetation is not the only type of land cover that responds strongly in near infrared and very weakly in red. So if I use infrared alone, or if I use red alone, I'm subject to mistakes, okay? The story changes a little bit if I use them in a combined manner. This is yet another very simple elementary example of data fusion, if you wish. In this case, what I may want to do is to take two bands from the same acquisition and specifically take the red band and take the infrared band, and then their ratio. Because in this case, I can, if I take the ratio of the infrared value divided by the red value, I have a variable, a computed result, which is very high only when I have high value in infrared and low value in red. So basically, I'm taking an eye on both items, on both features of vegetation at the same time, which makes me much more confident in concluding that I'm looking at vegetation or I'm looking at something else. Okay, so like for example, I have this Sentinel-2 image. This is India. Again, this is Mangalore in Karnataka. This is an exercise that I made there a few years back, and it's still very useful. I took this image. It's very good because it shows you that, I mean, if you take, this is band 3, green, okay? As I said, when you search for vegetation, when you're after vegetation in remotely sensed data sets, multispectral data sets, for sure vegetation is green, but don't search for green objects, because if you look carefully, you may notice that, well, there's so much green, and Mangalore itself is greener than the actual forested area here. Look at the data set. You're simply measuring reflectance in the green band. So vegetation is green, but the city is greener. Not to talk about the cloud up here. It's even greener. But it's not green, actually. It's that the cloud is very reflective in a broad range of bands, and we are only picking up the green. But as a matter of fact, if we limit ourselves to thresholding on green, we will pick up the cloud, we'll pick up the city, and then maybe also vegetation. Why? Because we're taking a very ineffective approach here. We're looking at green. We should be looking at infrared. So if we look at near infrared, then things start to straighten a little bit. Vegetation is actually more infrared than the city. Does that make sense to you? If you look at this image, I noticed that the vegetation, which is further inland, is greener than the coastal city, right? So I'm on the right path. But I can do better because the cloud is still more infrared than the vegetation that I'm interested in. So this is why we took the other band, which is red band, where vegetation is dark because you remember there's this dip in reflectivity. So vegetation is dark and it's also infrared. So if we take, and the cloud also, so if we take the ratio between near infrared and red, this variable, this ratio, is only high when at the same time you have strong near infrared response and weak red response. And in fact, in this map, you will see that patches of vegetation within the city are visible. Plus, all this area, which is heavily vegetated, is all clear. And all the areas, including your cloud, which were responding strongly, has actually disappeared because of the ratio. Okay, so one more very simple way of extracting a feature with a spectral meaning, which shortens your path to finding the result. In this case, with a couple of very simple operations, you have found a way to roughly separate vegetation from other types of land cover, even from clouds. And specifically, this feature is called ratio vegetation index, or RVI. One thing I can mention here very briefly, so we don't have to go over it again later, it's the fact that from this feature, another one important feature in the context of Earth observation is derived, which is called NDVI, or Normalized Differential Vegetation Index. NDVI, because this feature has an issue which is linked to having red at the denominator. You're searching for vegetation, so you're searching for something with low values of R. But R is at the denominator, so you're putting at the denominator something which is small exactly when you have your land cover class of interest, right? Which makes the measurement, which makes the feature unstable, because you're putting a small number at the denominator, so the errors will be amplified. So once they realized this, scientists came up with a new index, which is called NDVI, NDVI, Normalized Differential Vegetation Index, which is basically NIR minus R divided by NIR plus R. At this normalization, this very simple operation of normalization, see, it's a combination of the operations that we have seen earlier. By combining these operations, you get a much more stable index, which is confined between -1 and +1, not 0 to plus infinite like here, but from -1 and +1, which behaves in a much more stable manner. That is also a feature that can be extracted from a remotely sensor, from a multispectral data set, and that is a very popular and very useful type of feature. Okay, so these are spectral. This index that I just described is based on spectral information. Thank you. Thank you so much. But yesterday we discussed leveraging not just spectral information. This is spectral information. Do you agree? I'm leveraging spectral information in this case. Why? Because I'm using the properties of the spectral curve. I'm not looking at the neighborhood. I'm not looking at spatial patterns. I'm blind. This operation is blind to spatial patterns. It only uses spectral information. So this is a spectral index. Okay? Remember this because basically the distinction between spatial and spectral floods largely out of simply saying one is about spectral response and the other one is spatial. It comes to characterize practically all of the operations that you do. And this particular operation is in the spectral domain, because I'm using the shape of the spectral curve to derive this. But what if I want to leverage spatial information instead? Okay, that's where, for example, filters come into the game, because filters are designed exactly for doing that. I'm talking about spatial filters. Those of you who may have background in signal processing may know about filters, where the independent variable is time. okay? Sure. In this context, we're talking about filters, talking about linear time invariant blocks where the independent variable is not time, it's space, and it's two-dimensional, and it's sampled. But the principle is the same. Okay, we have an independent variable which supports the signal, in this case a sampled signal, because remember we're working with raster data. Raster data is discrete. It's made of individual samples. Okay, but the reasoning is the same. So what do we do with filters? So now it's difficult to make a consistent and satisfactory discussion of this topic because some of you who have experience of this concept may find it boring, but others may not have a clue of what I'm talking about because this is really signal processing. But anyway, filtering means performing a linear and, well, not necessarily linear. There are also non-linear filters, but let's focus on linear filters because this is somehow complex. Carrying out a combination of, I'm thinking, okay. Is it okay? I mean, I'm not making you skip your lunch. Okay. Okay. So let's keep it to higher level. Obviously, if you look at the formal definition of the filter, I mean, if you have no experience with it, you can find it a little bit unpleasant. But still, the concept, okay, so this is for those of you who know about signal processing. The idea is similar. We just change it, the domain in which we apply the concept, but the concept is still there. But in practical terms, what we do is we have a sliding window. So we consider local neighborhoods. We only look at a specific section of the data at a time, but then we slide that section across the entire data set, and we carry out an operation, a linear operation on each and every possible location of this local neighborhood, and we put the result in a new data set that we call the filtered data set. Okay. Depending on the operations that we do when we are hovering over a certain area to find the result that we place in the second data set, depending on that, you have a different meaning for this result and different features that you may be extracting. So let me cut the story short because we don't have much time to discuss it. The idea is that with this type of data, I will illustrate it with an example, which is the fastest way to pass the concept on to you. This is one more excerpt from the previous data set of Mangalore. This is the original visual representation of band number 4, which means green. You see the cloud is there, the part of the city is there, it looks familiar. What can I do with filtering on this image? Let me take a couple of very common types of filter. I said filtering is about spatial features, it's about spatial information. So one very simple thing we can do with spatial information is killing very fast spatial variability, which is called low-pass filtering. So if we tune in a suitable manner the operations that we do on the local neighborhood, we can suppress local high variability, high spatial variability. Okay, so we can do like this. This is the same data set, low pass filtered. What does that mean? It means that in every local neighborhood, I hampered the local variability. Okay, so I basically dragged values closer to each other. So I smoothened the image. Why is it called low pass? Because it kills highest, so only low spatial frequencies are left to survive, whereas the higher spatial components of the image that have spatial frequency components of the image which are responsible for sudden edges are killed. So the image is blurred. Why is this operation interesting? Because, well, there are various possible reasons why you want to do this. One of the most common is because this is a quick and dirty way to reduce noise. Remember, we discussed noise and the fact that averaging can reduce the impact of noise. Well, you can do that temporally. So you can do that by combining together multiple acquisitions in time, which was the subject of the previous discussion, or you can do that by averaging spatially. This amounts to a local spatial averaging. If I'm sitting here and this is a vegetation pixel, it's likely that the next pixel will also be vegetation and will also be of the same type, more or less. So if I average them together, because they're sitting close to each other, see, so there's a high probability that they are of the same type. So if I average them, I'm implementing a quick and dirty way to reduce noise. Obviously, I'm also, it's dirty, it's quick, but it's dirty. So if this is vegetation, but this is bare soil, I'm generating errors. So don't rely too much on this. But still, be aware that you have this tool at your disposal. On the opposite side, if you tune the operations in a different manner, you can do the opposite. So it's called high-pass filtering, which means I kill the low-frequency components and then let the high-frequency component to pass. What are the high-frequency components? It's the edges. Okay. Edges are spatial features. So with this type of filter, I'm extracting spatial features, which I can find useful to, well, to distinguish the non-homogeneous, non-spatially homogeneous urban area from the spatially homogeneous sea. Well, don't kill me. Just one very last point. All these operations, again, are about spatial information. In this case, I killed the average, see, because the average is not an edge. I suppressed it. The sea is darker than the urban area. But if I high filter it, I cannot see it anymore. This information went lost because this information was sitting in the low pass component, was sitting in the average of the image, right? And the high pass component killed it. The high pass filtering killed it. And this is a case where classification of the lens cover can be done based not on the spectral response, but based on the spatial information. Okay. If you look at this image, what did we do? Suppose this is an intermediate step in a processing chain. I acquired this data set, and I took one of of the bands because I'm not interested in spectral information. I don't want a spectral response. I focus on spatial information. So I take this because I know that the city comes up with different spatial features with respect to the other types of land cover. So I apply high-pass filtering, and I can look at this stage at some local indicators of for example, the number of edges, and then I can tell this is an urban area and this is the sea. And I have never used, in this process, I've never used spectral response. Does that make sense? Makes sense to you? So when you, for example, when you think of an application like land cover classification, you may decide that you leverage spectral response, if that is appropriate, or you may decide that you leverage spatial response, spatial information, if that is appropriate, or you can also use both. Okay, the path may be more complicated, but be aware that there's also this opportunity. So with respect to what I told you at the beginning, so use spectral response to identify the material, yes, that's one possible way of approaching the problem. But your problem may benefit from spatial approaches as well. And then I will stop here. I don't want to take any more of your patience. Thank you.